Hi, Paul.
Hi, Bob.
How are you doing?
I'm doing very well, thanks, here in sunny Arizona.
Yeah, I envy you. I envy you. It's not only sunny but dry.
Yes, and this
That's
time of year the weather's magic because
yeah.
it's not too hot either.
Well, you don't have to mind us. It's a kind of a humid day on the eastern seaboard here, and hot for late September. But let me introduce us. I'm Robert Wright. This is the Wright Show. You are Paul Davies, very well-known physicist. You've taught at a lot of places, including Cambridge. You taught in Australia for a while.
That's right,
Um, eh,
University of Adelaide, and then in Sydney at Macquarie University, and I'm
mhm.
now at Arizona State University.
Right. And you've won a lot of prizes named after eminent people: the Kelvin Medal, the Faraday
Yes.
Prize, the Templeton Prize. You've also won something called the Eureka Prize, not once but twice, which I'm sure is a source of chagrin to those of your colleagues who have only won the Eureka Prize once. I've won it 0 times, so congratulations on that. You've also written a ton of books. I mean, you've written academic books, technical books, but a lot of popular books that you're very well known
Yes,
for.
yes, I say a lot of popular books and some unpopular ones as well.
Well, I'm not gonna. I'm not in a position to make that distinction myself. I'll leave that to you. But I did want to. What I thought we could do. You've written so many books that I just wanted to name some titles and do kind of free association because it seems to me. I mean, some of them I have read, some of them I haven't, but some of the titles are so suggestive that I thought if I just name a few titles, we talk about what they mean. We would, by the end of the conversation, have covered virtually every aspect of physics anyone could ever want covered. Although time may run out, but we're not to that constraint. I think we could do the job.
Good.
So I want to start with one I have not read called the Matter Myth. Now, is you tell me, is matter a myth? Um, it is. What did you mean by that title?
Well, I think so. First of all, this was a book written many years ago, so uh, any of our viewers wanting to find it may be faced with a bit of a challenge. But the overarching theme there is that when we look at solid objects around us, tables, chairs, and so on, and then ask what's really going on there, as you dig deeper and deeper into them, you find that the concept of matter as we understand it in daily life just dissolves away, first of all, into ghostly patterns of vibrating energy that we associate with quantum mechanics. Then there's a lot of just empty space. But then we find that empty space itself is filled with a sort of seething ferment of what are known as virtual particles. This is something else that comes out of quantum physics. These are particles that are not quite real, but they still have an effect. And it goes on and on and on. And even when you get right down to the ultimate structure of space-time, you find that that dissolves away into a sort of foam or a riot of wormholes and
Wait,
bridges.
space and time itself does, or just everything that
That's
fills it?
No, that's correct. Even space and time, we like to put them together, since Einstein told us we must do that.
Right.
And so we talk about space time. And there was a very nice metaphor used by John Wheeler, one of the great physicists of the 20th century, that if we think of space time just by analogy with the surface of the ocean, this would be a two-dimensional analog of four-dimensional space-time. And if you're an aviator flying at 30,000 feet above the ocean, it just looks like a sort of flat plane. Or we may see the curvature of the Earth, it may be slightly curved. And then as we get down lower, we begin to see there are waves. And as we get down even lower, we see that some of those waves have froth. And he feels that that's a good way of looking at space-time. If you get down to a scale about 20 powers of 10, smaller than an atomic nucleus, the apparently continuous nature of space and time that we infer from daily life breaks up into complicated topological features, and it's all shifting around. These are virtual wormholes, bridges, and virtual black holes. Virtual in the sense that they can pop into existence, but only fleetingly, and pop out of existence again. So a whole notion of solid matter located in some sort of immutable void, which is the way the ancient Greeks looked at it, just dissolves away. Both the matter and the void dissolve before our very eyes when we peer closely.
Now, is this where quantum physics takes over? Because I know there is this fundamental problem that at very small scale, quantum theory works, right? And do I have this right? And at larger scales, relativity works. Is that related to what you just said? That at very small scales, the very fabric of...
Yes, sort of. Now, the first thing I should say is that most physicists would say quantum mechanics works on every scale of size. It's only that its effects are most manifest on the small scales, atoms and molecules and below. So that's not completely settled, but that should be stated. And then when it comes to relativity, of course, we have to distinguish the special theory of relativity, which really governs how objects behave when they move close to the speed of light, from general relativity that involves gravitational fields in addition. And the point there is that unifying special relativity with quantum mechanics was already done around about 1930 by Paul Dirac, and that really concerns the realm of fast-moving subatomic particles. So, for example, the Large Hadron Collider at CERN, very much in the news in these last few years with the discovery of the Higgs boson. This is a world in which subatomic particles, in that case protons, are hurled around a tube 27 kilometers in circumference, very, very close indeed to the speed of light, and then they smash into each other and make all sorts of subatomic fragments. And this world must be described by both special relativity and quantum mechanics. So those two are unified in that type of experiment or that type of experience. Cosmic rays would be another one. If we bring in gravitation, then this gets much more problematic because then that is a theory that's often quantum gravity, and this is famous for being one of the most picked over and least agreed aspects of physics that remain unresolved. And there was a contentious merging. I think the general theory of relativity that Einstein gave us in 1915.
Okay, before we get to that, let's get back to this matter question. The thing we started with, that the intuitive notion that ultimately there is this physical stuff called matter is in some ways misleading, because if you get deep down enough, it doesn't look very much like matter, right? And of course, I think most people have some familiarity with quantum physics, where at that level, it's not even clear whether you should call something a particle or a wave in some sense. Do you think, there was an essay written in the magazine, the online magazine Aeon recently, by an astrophysicist at the University of Rochester named Adam Frank. And he was calling into question whether materialism is really the right word for science. Of course, we often hear scientific materialism, and materialism is taken to be almost synonymous with a scientific worldview. But do you think we should question terms like that at a fundamental level?
Yes, absolutely, because what we think of as material in daily life, and the word materialism really goes back to the 19th century, maybe even earlier, is that view of the sort of solid stuff, material particles, and that I think when people use it pejoratively, it's if we're talking about things like human emotions, and if you're a materialist, you want to reduce that to the activities of particles, and then that sort of looks as though somehow you've lost something on the way, or it's a sort of bleak view of nature. But of course we do know, as I've explained, that that matter is not just little lumps, as the Greeks thought. See, so the the Greek atomists had this notion that the world was nothing but particles moving in the void, and that everything that happens is just the rearrangement of those particles, and that there's really nothing more to be said. So everything that happens, including our finest thoughts and emotions, just boil down to the rearrangements of particles. And very few people who I think would be very satisfied with that. Whether it helps to say, well, these particles themselves are much more nebulous, and the relationships between them are much more subtle, I don't know. There is still a huge disconnect, an explanatory gap between the world of quantum physics, where things are fuzzy and uncertain and it's indeterministic, and the everyday world of experience, when we make observations and see apparently a single concrete reality. And this is an unresolved issue at the foundations of physics. Right. It doesn't affect the power of quantum mechanics to give us things like the laser and the transistor. It works brilliantly in explaining the world as a mathematical theory. It makes very specific predictions, and it's never let us down. But in terms of what does it mean as the nature of reality, that is still very much up in the air.
And in a way, it's not just a question of whether, the stuff, the ultimate, stuff at a very fine-grained level really feels like stuff. I mean, one could say, well, okay, of course it's not matter in the sense of particles. I mean, we always knew it could be converted to energy, which sounds more amorphous to begin with, but the main thing is that there is regularity and predictability. But even that, in a certain sense, breaks down at the quantum level, because the predictability becomes valid only in the aggregate statistical sense. There are individual events you cannot, in principle, predict with scientific laws.
Yes, that's correct. So I often say, you can fire an electron at a target, it bounces to the left. You do the same thing again under identical circumstances and it bounces to the right. Quantum mechanics can predict what that ratio might be. It might be 50-50, for example, and you do it a large number of times to test that. But in any individual case, you cannot tell in advance which way it's going to go. And we believe even nature doesn't know which way it's going to go. Mm-hmm. That is, this is an indeterminism not born of ignorance, like the toss of a coin or the outcome of roulette. That's because we don't know enough about the factors, many factors affecting its behavior. But we're saying quantum mechanics, this indeterminism or uncertainty, is intrinsic to the system. And so even Mother Nature does not know.
There are things that happen that have no cause in the physical universe in a certain sense.
We could say that they are genuinely spontaneous. Again, my favorite example is if you take a uranium atom, take a chunk of uranium, it's got a half-life of 4.5 billion years or so, which means if you have 4.5 billion uranium atoms, there's a good chance one of them will decay in a period of 1 year. But if you spot that one decay, and you say, well, why did that atom decay and not the one next to it? There is no answer to that. It's just intrinsically spontaneous and indeterministic.
Okay. Let me, as long as we're at deep levels, where kind of, I guess, physics bumps up to metaphysics, let me mention a more recent title of yours that is an academic book. It's Cambridge University Press. It's Information and the Nature of Reality is the title. The subtitle is From Physics to Metaphysics. Now, I think almost anything you say about this book will be hard for people to understand, I suspect. But one thing I want to say is that, let me prompt you with something that Brian Greene said on this show recently. We were talking about kind of, well, what is the ultimate nature of stuff? And he said, well, some people like to think of information as being the most fundamental stuff. But he pointed out, everything we know of as information in our world, news, print, sound waves, and so on, is made up of physical stuff. So it's not that easy to imagine information being fundamental, and yet some physicists like to talk this way. Is that right? And maybe you,
yes,
for all I know.
That's right. No. This is something that I'm very much involved with in my research here at Arizona State University, and we have conversations like the ones we're embarking on now several times a week, because I think the thing about information is that it is a fundamental and unifying concept. We see it in physics, one way you can think about that, even in quantum physics, we just discussed about an electron might bounce to the left, it might bounce to the right. You could do the experiment and not look, and then you wouldn't know. But if you decided to look, you're asking nature the question, is it to the right or is it to the left? And then you'll get an answer, say to the right. So that's very much like one bit of information being acquired from interrogating nature. In the absence of that interrogation, we can't say much about it. So at that level, but then as we go up through biology, everybody knows that a gene is a set of instructions to build a protein. So that's not only information, it's information that has some sort of meaning to the system, has some functionality. And then we go all the way up to the operation of the brain, which is surely an information processing system, very much like that. We're associated with computation. And so we see information at all these different levels, entering into physics and biology. I personally think it is the unifying concept that enables us to combine physics and it's just such a thing.
Let me interrupt you again, just because your voice is fading out a little here. Mentioning it may be the lucky charm that solves the problem. Who knows? But
yes, I was again hearing that weird sort of rushing sound.
Yeah. Well, now you sound fine. So let me let me pursue that just a little bit further. So I mean, again, I guess what Brian Greene would say is, well, yeah, but at the level of the brain and the level of the gene and so on, that's information made of stuff. When you get down to that lowest level and say, when we interrogate nature, we receive information. That seems a little different, although I guess on the other hand, you could say that, look, the information is all we ever have immediate access to. I mean, what lies beyond is always conjecture in a sense. In other words, the bit of information you get when you interrogate nature, that's almost realer in a certain sense. It's more immediately perceptible to you.
And I already mentioned John Wheeler. He's very famous for an aphorism, it from bit.
Right.
So what he meant by this is that if you look very carefully, at least at the quantum world, that we traditionally have thought, well, there are particles of matter, like electrons and so on, and that information is a sort of secondary concept. But he wanted to turn that around and say, no, ultimately we get all of our information about when we interrogate the world. That's what we get, bits of information. And we infer the existence of particles of matter from that information. So it's really around the other way. We start with the information and abstract it into matter. Whereas I think in daily life we think matter is the real thing and the information is the abstract. But the important point I want to make is that information doesn't sort of float free in the ether. It's always instantiated in matter.
Right.
And so if you take a good example, the information in your computer is in material degrees of freedom in the chip and so on. But the interesting thing about it is the fact you can copy a file from your computer, say, into a flash drive, and then maybe send it in laser pulses up into space, something like that, means that this information is interconvertible. So it's got a sort of life of its own. It has a type of autonomous existence, although it must always be tied in some way, instantiated in some way, into material degrees of freedom, if we include light in the word material there, but physical degrees of freedom. And so in some ways it's a bit analogous to energy. We recognize that energy is a meaningful concept, and we know when we lack energy and when we need energy, and there's an energy crisis and so on. So it's a sort of thing, but we know that it's always got to be, again, instantiated in physical objects, but it can be traded. It can be gravitational energy, can be the heat energy and chemical energy and so on. It can be passed around and in a conserved way. And in the same way, information can be passed around. And so I don't think we yet have a full grasp of how to put together the laws of matter and the laws of information in a way that fully takes into account the miracle of life and of mind and so on. Because we sort of recognize that there, information is somehow calling the shots. It seems to have causal efficacy over the physical system. Yet we know ultimately that the laws of physics must still be respected.
Yeah.
What is not clear is whether one day we'll be able to sort of unify these two without anything new, or whether we really do need genuinely new laws and principles. And I'm sort of fascinated by the idea that there may be something missing, and that find it in this overlap between physics and biology.
Yeah, well, it's interesting the way when you talk about information being fundamental, you start talking about the relationship between the observer and the observed, and that has appeared elsewhere in quantum physics in some explanations of like what's going on when you measure something, and then it seems to assume a clarity of resolution that it didn't have in the meanwhile. The act of measurement seems to, some people there have invoked. I don't think most physicists have, but some people there have invoked the kind of witnessing being, the person.
Right. The entry into the consciousness of the observer
Right.
collapses the wave function is the term that has been used. And this is very much a minority of physicists. It began with John von Neumann. It was most famously championed by Eugene Wigner back in the 50s, I guess, 60s. It doesn't have many takers, I have to say, that there are other interpretations of this measurement process, but they're all equally challenging. So, for example, one that was very much on the fringe when I was a student, but now seems to be the mainstream, is the many universes interpretation. So what's happening here is the electron's going along. Does it bounce to the left? Does it bounce to the right? The answer is it does both. That there are two universes, one with a left moving electron, one with a right moving electron, and each has their observers. The observers in the left moving one see it moving to the left, and same with the right. Each thinks that they're unique, but they're not. That there are infinite number of observers in these parallel worlds. Now, you might think this is very extravagant too. Wouldn't it be easier to invoke the mind in some way? And that is
the two seem about equally outlandish to me personally, but actually, I think, am I right that more physicists or maybe more philosophers of physics these days take many worlds seriously than take seriously the idea that consciousness is in some sense influencing the reality?
You'd be correct. Almost all of my physics colleagues would opt for the many universes interpretation. They wouldn't like the idea of consciousness. I have a little corner of my consciousness still would like to retain the option of embedding consciousness somehow in the quantum description of the world, because it seems to me that we should take consciousness seriously, not just try and explain it away or remove it entirely from the story of quantum mechanics. Because if quantum mechanics purports to explain the whole world in its entirety, it needs to incorporate consciousness somehow in its description. And it seems that by going to this opposite extreme of this many universes interpretation, we've lost the opportunity to actually understand consciousness at the scientific level and incorporate it into some maybe adapted description of quantum mechanics. One or two of my colleagues have tried to do that, but mostly they would just go down the many universes path. They didn't. When I was a student, that was considered a bizarre interpretation, but now it seems to be the party line.
And the main alternative to a non-outlandish interpretation of quantum physics, in other words, so like many worlds or consciousness or something equally strange, is to just decide not to think about it, basically. I mean, the Copenhagen interpretation is kind of an agreement, just not to worry about the philosophical implications, right? Right.
So now, I have to say that most physicists just get on with the job. They don't lie awake at night worrying about what is an observer and how does the wave function collapse. They just solve the Schrödinger equation and might be interested in the properties of some material, and there may be some commercial outcome, and it all works brilliantly, and you don't need to get yourself into that. But people like me do lie awake at night worrying about it. There is another way out. And that is to say that quantum mechanics doesn't apply all the way up to the universe. So there is some point where the physics changes from the quantum world to what we call the classical world, the everyday world. And the difficulty there is that we have to then introduce something new. And so proponents of the many universes interpretation say, well, we just need quantum mechanics. We don't have to invent any new physics. We just take it as it is, and it tells us there are all these different branches. If you want to have something new, then how about this? There may be a system not sufficiently large in physical dimensions, not sufficiently massive, but sufficiently complex, might have different rules, different dynamical behavior from a simple system. So a brain is certainly complex enough to make a big difference. A cat's brain is, to use a famous example, is probably good enough, and maybe even a complicated bit of equipment. But that it would be when you got down at the level of the hydrogen atom, everybody agrees that it's quantum mechanics reigns supreme. At the level of a brain, you might want to think there's something different going on. Somewhere in between those two, there would be a threshold of complexity at which the rules of the game would change at the dynamical level. That is, the wave function is the term we use, or the state vector is the term we use for the actual description of how a quantum system changes with time. It changes according to Schrodinger's equation. Schrodinger gave us this equation in the 1920s. That maybe that equation, some additional features enter that equation at a system sufficiently complex. That's a very minority idea. I think it probably is just me, maybe one or two others. But I floated as an alternative to some of these other rather weird things.
Well, to maybe, let me ask a question that may or may not be closely related to that, depending on whether or not I'm understanding things. And this question is also suggested by another book, this one you edited, called Quantum Aspects of Life. One thing I've wondered is, people have long wondered about free will and determinism, and whether quantum physics could play a role in the free will question. And I would think that would depend partly on whether there are quantum events in the brain, undetermined quantum events in the brain that have, important manifestation at the macro level, right? That actually shape a behavioral path. Now, what is the thinking on that question?
Right. So first of all, there's no unanimity, but secondly, there are a couple of things there that need to be said. I think the classical argument against free will is, if we live in a deterministic universe, if you're made of atoms and the world around you is made of atoms, and atoms do what atoms have got to do, then everything is already determined right down to the smallest wiggle of your little finger. In advance, in fact, forever, determined backwards and forwards in time. And that was a famous statement by Pierre Laplace back in the 19th century. So there seems to be no room for free will. How could you have a choice? How could you steer your future if it's already laid down in the pattern of behavior of the atoms that make you up and you're around you? And so determinism seemed to be the enemy of free will. And then along came quantum mechanics, and people said, the world is actually indeterministic at a fundamental level, so doesn't that open the door to free will? Well, it's a two-edged sword, because on the one hand, yes, you're not in this deterministic straitjacket, but on the other hand, you don't want an arbitrariness to enter. You don't want to think to yourself, I'd like to move my arm, and your foot moves instead. You would like to think your will determines your action. So whilst it sort of loosens the cause-effect reins, it doesn't quite do the job.
Although, let me, I'm going to ask you a question that's kind of like one I asked Brian Greene, but is a little different. But the premise is the same. It begins with the argument that these quantum fluctuations are only random so far as we know. In other words, like we know that, say we've got 6 events, we know that 3 are going to turn out heads and 3 tails. I mean, the larger the number, the more confidently you make the prediction. But the point is, there is something confident you can say about how the ratio will wind up between the events. Yes. But you don't know. I mean, suppose just conjecturally that my will, and I actually asked Brian a different question about this, but suppose that my will is the thing. I mean, maybe it matters. I've got these 2 outcomes. One has to be heads, one has to be tails, let's say, to oversimplify. and my will gets to choose whether this one's going to be heads and this one tails, or this one heads and this one tails, and those two outcomes would lead to different behaviors. Now, physicists would not be able to detect that anything is making that decision, right?
That's right. So what you're describing is certainly possible, and there's nothing in experimental physics that would contradict that at this time. It would not, however, be quantum mechanics, because of course quantum mechanics requires that if you do the thing many times, you'll have a certain
right. But what I'm saying is, it's like the analogy is like with a roulette wheel, where you know that in the long run it has to hit 2 as many times as it hits 3. But if you can be under the table with a magnet deciding that this is the time it's going to hit 3 when somebody's got a lot of money bet on 3, and this is the time it's going to hit 2, that would be indiscernible to the physicist, so to speak, because the stats would come out the same way, and yet it would be a decisive intervention.
Right. Yes, it would. But now it depends on your understanding of free will. But if that understanding is you are faced with a choice and you choose A over B, I think most people would feel that it would be only meaningful to call that free will if, when you were faced with the same choice again, you would make the same choice. Because otherwise it would just be arbitrary. You just think that you'd chosen, but actually it was some, just some fluctuation that caused it. And if you were to literally do the experiment again and again and again, you would contradict quantum mechanics, because you'd find that you wouldn't comply with the probability.
Yeah, but see, I don't think you would. I'm probably failing to make myself clear. I mean, Brian actually agreed that this would not defy quantum. Except the question I ask him is: suppose it's a god out there with a magnet under the table, and again, you're not changing the overall probability distribution. You're just saying, instead of this one being heads and this one tails, I want this one to be tails and this one heads. The aggregate numbers come out the same, but it makes a difference.
If these are unique events, of course, we can't distinguish between them. And I think we would recognize that, for example, this conversation isn't going to be happening a second time in the universe. So it's not like we can say, well, quantum mechanics led to me to say this, and next time will lead me to say that. So if you don't have a distribution of identical systems where we can talk meaningfully about probabilities of outcomes, then of course there's nothing very much we can say. And so you can invent other things that for unique circumstances. You can say, there's nothing no experiment we could do.
Right, a unique intervention could be undetectable so long as it was kind of balanced out in the aggregate in a certain sense.
Right. There's something else I should say, though, in connection with this quantum brain stuff, which is it's a whole different set of issues, which is whether quantum mechanics is playing an effect in the brain in such a way as to explain some of the mental phenomena. And there's a minority of scientists, most famous Roger Penrose from Oxford University, who've suggested that if you get right down to it, you have to go down below the level of a neuron, because that's already too big, but in the microtubules that thread through the interiors of them, that there may be non-trivial quantum processes going on, and that could somehow explain consciousness or be involved in some way in consciousness. And very, very few scientists, I think, believe that, for the simple reason that the brain is a sort of warm and wet environment, and that the thermal agitation of the surrounding particles play havoc with the delicate quantum processes. However, we do know in biology there are 4 or 5 phenomena that really do seem to depend in a non-trivial way on weird quantum effects. One of these is photosynthesis, another involves electrons tunneling through organic molecules, and then there's some evidence that the olfactory sense makes use of quantum effects. And so it could be the tip of an iceberg, and it could be that we will need quantum mechanics. There'll be a sort of life principle embedded in the small print of quantum mechanics, and that one day we'll discover that quantum physics is indispensable to understanding life, that it actually incorporates life in some way. We haven't found that yet.
Right.
Or we found a few quirky cases. Whether the brain is part of those quirky cases, I don't know. I'm a little skeptical myself, but I keep a corner of my mind open for that.
Okay. So, keeping the conversation at a level of fundamental questions, you started a controversy a few years ago with a piece in the New York Times called "Taking Science on Faith."
Yes.
Maybe the controversy started with the part where you said that scientists have a certain kind of faith in the kind of immutability of laws or something. But you also, leaving aside the question, I'm sure the standard reply was, but this is faith based on experience or something. But leaving that question aside, you also said, let me quote this, the laws should have an explanation from within the universe and not involve appealing to an external agency. The specifics of that explanation are a matter of future research. But until science comes up with a testable theory of the laws of the universe, its claim to be free of faith is manifestly bogus. Now, what do you mean by that exactly?
Well, you can't be a scientist without making two assumptions about the world. One is that it's at least in part intelligible to us. If you thought it's all just meaningless jumble out there, you wouldn't embark on science. You expect as you dig deeper and deeper, you'll find some sort of meaningful connections. And the classic example is the Large Hadron Collider. They didn't spend $8 billion without some expectation that whether the Higgs boson was there or not, whatever was found would make sense. So you have to believe that we live in a rational, intelligible, ordered universe. You've got to believe that this order is really out there and it's not just an artifact of our culture or something. So a really existing law-like mathematical order in nature, that is the founding assumption of science. Now, we codify these in laws of physics. And if you ask physicists, well, where do these laws of physics come from? How do they originate? You're usually told, well, that's not a scientific question. Don't ask that question. Or that makes me feel uncomfortable. Or let's just get on with the job. We write down our best guess of what these laws might be, and then we just use them and do physics. But I'm interested in where those laws came from because and why they are as they are. They could have been different. They could have been no laws at all. So we live in a universe that's got these very special laws, and it seems very natural to ask where they come from. But if you don't want to do that, if you just want to get on with the job, then you accept those laws on faith. By faith, I didn't actually choose the title of that article, but I'm prepared to defend the use of the word faith in the same sense as one might remain faithful to one's spouse. What it really means is that you take depend on them. You depend on their veracity of these laws. You can't prove they have to be as they are. You can't even prove that they're the correct ones. You can try and disprove them. And so embarking on the scientific endeavor in the belief in a rational, law-like, meaningful order is the founding assumption of science. And it actually comes straight out of monotheism. When you look at where it comes from, the Galileo, Newton, and these early scientists, they were all Christians and some Jews, and before that was the Muslim tradition. That we have here a combination of Greek philosophy with its emphasis on humans can come to understand their world through reasoning, combined with the notion of a created world order that could have been otherwise, but is as it is because it was ordered that way by a law-giving deity. And science simply adopted that view. They killed off the deity, but they adopted the view that the world could have been otherwise, but is arranged in this rational, intelligible manner. So the purpose of that article was really, I was wanting to call in question after 300 years of this philosophy, whether we should get away from the idea that the laws of physics are indeed immutable, imprinted on the universe at the Big Bang, at the outset, and are unchanging, and we don't question where they come from. And actually say maybe the laws and the universe somehow co-evolve in a manner that I tried to tease out in my book called Goldilocks. What's odd about these laws is the fact that they're so bio-friendly, and that causes a lot of grief among scientists trying to explain that.
There we're getting kind of to the anthropic principle, as it's called.
Right. Yes. So it's we look at the laws that we know and understand, and we can ask why are they as they are, and could they have been otherwise? And if you think they could have been otherwise, then you might wonder. Your next question is, well, supposing they've been different, how would the world be different? And we don't have the budget to do the real experiment, but we can do the theoretical experiment by taking the laws of physics and changing some of the features in those, and then exploring what the consequences of that would be. And it's been known for many, many years that some of our laws couldn't be changed by very much, and without wrecking the universe in the manner that we see it. So what do I mean by that? Well, I suppose you don't like the laws of physics as they are. You'd like all electrons to be a bit heavier, or also the weak nuclear force to be a bit weaker, or something like that. What would happen? And the answer is a lot of very dramatic things can happen, quite small changes in those. And then the preferred explanation is, well, the reason that we live in a universe that looks like it's rigged in favor of life is because there's an infinite number of universes. So we're back to that, but this time an infinite number of universes each with different laws, and that only in a tiny, tiny subset will all those features come out just right so life can emerge. And it's no surprise we find ourselves in a bio-friendly universe. We couldn't exist in a sterile one.
Right.
That's the anthropic.
Right. Now, I know we're running up against the time constraint that you're in, but I can't help but ask one more question, because you talked about like where the laws come from, and I know a colleague of yours at Arizona State is Lawrence Krauss, and he and I have argued about the book in which I think he claimed to have settled the question of why there's something rather than nothing. Now, you're probably familiar with this whole thing, right?
Yes.
Do you consider?
Well, I don't think that question is by any means settled. I mean, there's the trivial answer. There are many ways for there to be something, and only one way for there to be nothing. I think what Lawrence was anxious to do in his book *Universe from Nothing* was to talk about how the universe could come into being without there any prior existence of space, time, or matter. And he's absolutely right, and I say exactly the same thing in the Goldilocks, Enigma, and my other books. However, the big difference between us is that he's prepared to take the laws of physics on faith, as an act of faith, and the laws of physics can bring the universe into existence. I would like to know where those laws of physics...
This was what I said to him. If there are laws that can account for the emergence of anything, then there wasn't nothing to begin with. There were laws. That's not nothing.
That's right. And that's where he and I would probably part company. And of course, someone in his position could always say, well, asking where the laws come from is not a scientific question, and I'm going to ignore that. And so we're back to,
it's a philosophical question, but he purports to be addressing a philosophical question.
Yeah, and I actually think we can push the scientific agenda to the point where we can incorporate the origin of the laws in the scientific program, but that's very ambitious. And
now, are people knocking at your door, or do you have time for one more very quick question?
We do, and I should say also my battery is running low. So
okay, so if you die in mid, then we will promise people a sequel down the road. If you die in mid-answer, the question is just this: one question one could ask is, what enforces the laws of physics, right? I mean, in the real world, everything we call a law has an enforcer. Laws of society have police enforcing them. Laws of software have, we structure things such that we harness the laws of physics to make sure the electrons comply with the logic of the program and spit out the right answer. Isn't it kind of a valid question to say, wait a second, given that there are laws, what makes matter and energy comply with them? When you think about it, it seems kind of magical.
Yes. Again, the traditional answer was that there is a timeless God who underpins the universe at all moments and upholds the lawfulness. And so the laws are held into being by this deity. That's just pushes the problem off into some transcendent realm. And so that's not very satisfactory. I think your problem begins to be lessened if we get away from the idea that these laws are strictly immutable. And again, what I tried to do in the Goldilocks Enigma was to come up with the idea of a theory of everything, in which the laws were part of that theory of everything, where laws and matter and observers and space-time, all of these things were in an explanatory loop. Everything explains everything else. That sounds a bit mysterious, and it's not. I didn't do any more than set it out as an agenda. But I think your question is a very valid one, and it won't go away so long as we have the idea that these laws are sort of absolutely fixed for, as John Wheeler loved to say, from everlasting to everlasting. He liked the idea that you put the laws into the melting pot too. So we really want some bigger vision that brings the laws into the picture and doesn't just assume they're there as a dependable background.
Yeah. Okay, thank you. I wish we had more time. The reason we don't is because I actually had tech issues at the beginning of this, so I am the one to blame. You know, you have a lot of books that we didn't mention. I think you mentioned the Goldilocks Enigma, which it also appears under another title, Cosmic.
Yes, it does. It's very confusing. The
Cosmic Jackpot. But How to Build a Time Machine.
Yes.
You've written about the origin of life. You've written Are We Alone, about extraterrestrial. You know, so there's
but
plenty.
More recently, the Eerie Silence, which is a celebration of SETI, the Search for Extraterrestrial Intelligence, celebration, but also critique and a call to arms to enlarge the vision of looking for life elsewhere in the universe, and intelligent life in particular.
We could have a whole conversation about that alone, and I hope down the road you'll have time for another one, because this was a lot of fun.
I'd very much enjoy it. Please invite me back.
Okay. Yeah, I guarantee it then. Thank you so much, Paul.
My pleasure, and I'll say goodbye.
Okay.